So first of all, let me thank you for organizers for giving me this opportunity to give this talk. And as Professor Vladimir Žižek mentioned, unfortunately, Professor Jurga, who's supposed to have this particular lecture, he couldn't be with us today, and we do sorry all of you for these changes, but I will do my best to share our data, and I will try to explain it clearly, hope. And the topic remains the same. I mean, copolymer systems studied by NMR and other complementary techniques. So as you can see here, this building over there in this picture, this is our nanobiomedical center in Poznań, and we have quite nice facility over there, including NMR laboratory. We have 3 nice systems for spectroscopic NMR measurements, 600 megahertz, 400 megahertz, 800 megahertz machines, and besides we have also horizontal scanner for MRI measurements as well. And we combine these techniques with other spectroscopic techniques, and I will mention that also. For example, dielectric studies, broadband dielectric spectroscopy, we use it for, especially in the case of polymer studies, is very useful technique, and it might be nicely combined with NMR spectroscopy, and I will show some examples. I'm really glad that I can provide this lecture during this very interesting, stimulating conference. So let me start. So probably most of you have already heard about diblock in general block copolymer systems. So basically, these are, as it is shown here, the most simple example is that we have 2 different polymer species linked covalently, and this kind of macromolecule we can call diblock copolymer. And in early 90s, some theoreticians, they introduced this beautiful phase diagram, which was calculated for block copolymers, diblock copolymer systems, so for the simplest systems. And as you can see here, at the x-axis you have volume fraction. So what is the volume fraction of one component with respect to another? While on the y-axis you have this product, which is n times chi. Chi is a Flory-Huggins interaction parameter, which really gives us, provides us the information about the energy of interaction between 2 different subunits within such system. And n is really represents the number of subunits in the polymeric chain. So basically it is directly proportional to the molecular weight. So intuitively, when we have a volume fraction, which is 1:1, let's say 0.5, somewhere here, we end up with so-called lamellar system. So basically speaking, the very unique feature of this kind of systems is that they undergo microphase separation. So below certain so-called order disorder temperature, they self-assemble and they undergo microphase separation, which is this process is thermodynamically driven process, and then they form this very nice nanoscopic periodic structures of different morphology, different architecture we can see, and this architecture is very much depends on the volume fraction, as you can see observing this phase diagram. So as I said, for the symmetric block copolymers, we can expect this lamellar sandwich-like morphology, while there are also some other regions here, for example, assigned as with a capital C. They signify this hexagonally arranged in space cylinders, and for different volume fractions, where when the one volume fraction of one component is much higher than the other component, we can observe also the spheroidal morphologies. There's also quite interesting morphology which is here in this phase diagram, which is called bicontinuous gyroidal structure. It was, for the first time, it was described in the 70s by mathematician Alan Shen from NASA, and then he somehow discovered or defined this particular morphology, and later on it appeared that, for example, diblock copolymers, they can display this kind of bicontinuous, very unique morphology, which is very, very important, might be very important for microelectronics, for example, batteries design, because you can have this bicontinuous subspaces, let's say, where the ions can really migrate through the volume of your battery electrolyte, polymer electrolyte. So on the right hand side, you can see some experimental data. These data are these are examples from electron microscopy graphs. So on the top you have this hexagonally organized cylinders. In the middle you have the sandwich lamellar-like structure, and on the bottom you have the example of this beautiful gyroidal structure. And you can, what is the most important here is that these features are nanoscopic in size. So potentially they can be quite useful in nanolithography. And therefore, there are a number of engineers and scientists who are really focused right now to develop new strategies where block copolymers can be employed in the, let's say, modern nanolithography. So there are different approaches. One of them is, for example, where we can employ so-called directed self-assembly, because in microelectronics in particular, we would like to have these structural features nicely arranged, not only on the local scale, but also on the large scale. And therefore, sometimes we use some pre-patterned substrates in order to direct the self-assembling, because as you can expect, since this self-assembling phenomenon is thermodynamically driven, then of course we do observe some nanoscopic periodic structures on the local scale. However, these systems, they do not exhibit this long range arrangement, which is characteristic, for example, for monocrystalline systems. So we have to somehow help our amorphous phase to arrange in a certain way, and therefore this directed self-assembly is still being developed. So maybe for curiosity, this is a very nice example. I mentioned that this gyroidal structure was first observed in the case of diblock copolymers. They were able to develop this kind of beautiful structures. However, it has been shown that some species of butterflies, they do develop the same kind of morphologies like naturally. For example, the scaffold, which really constitutes the wing of this tiny fellow here, it does exhibit exactly the same gyroidal structure. And first of all, here you can say that, for example, the colors which you really observe are due to the structure itself. So that's the nice example where exactly the same structure can be spotted naturally. Well, here I would like to show you some of our results. On the left-hand side, you can see the picture taken by atomic force microscopy, and this is actually a thin film produced on top of the flat silicon monocrystalline substrate, and this is polyethylene oxide covalently linked with polystyrene with such a molecular weight, so 11,000, 36,000. And as you can see, we observe that we end up with a polystyrene matrix and some cylindrical polyethylene oxide domains. And locally, as we expected, we may distinguish easily this hexagonal pattern. However, that's the feature which I mentioned before, that on the large scale, macroscopically, this arrangement is rather distorted. So instead of having this quasi-crystalline long-range
добрый вечер.
Добрый вечер. Long-range
Микрофон выключен.
Long-range arrangement, we observe this organization on the local scale. And then there is a question how to introduce this long-range arrangement. So there is one trick you can employ. For example, the trick which is called the strategy which is called in general graphoepitaxy. So instead of using flat substrate, we use substrates which have some pattern, some structure present before the diblock copolymer deposition. And there is a very nice example where you can, for example, use sapphire monocrystalline substrate, which is miscut in such a way that you miscut the monocrystalline sapphire along so-called M plane, and then after annealing this substrate under high temperatures, your sample will undergo surface reconstruction, which leads to this sawtooth pattern arrangement. And what's nice about this structure is that it spreads macroscopically over the whole monocrystalline substrate. So you introduce some anisotropy, and which may somehow induce spatial ordering of self-assembled diblock copolymer domains. And this is the example. This is the result which we have shown, that exactly the same copolymer deposited on the reconstructed sapphire produces nicely organized domains in space. So that's for sure is a huge step. It might be a huge step forward. And for those who are interested in microelectronics and nanolithography, for sure, the long-range arrangement is the parameter which is crucial. And therefore, this particular technique might be used. And what is also nice, or maybe let me just add one thing, that using this substrate, structurally substrate, we slightly distort this hexagonal arrangement. It's not exactly hexagonally oriented. These cylinders are not exactly hexagonally oriented in space. There is a slight distortion, but only just a subtle distortion. And what is also very unique and interesting about this block copolymer patterning is that we can, to some extent, control the orientation of our domains at the surface of our thin films. And we can control them by changing annealing conditions. So this is a very nice example where initially we started with a slightly different, we annealed our thin films under slightly different conditions, and later on we changed the atmosphere, changed the gas, and we found out that we can, to some extent, control the orientation of our domains. So these three examples represent the same sample, I mean, the same material, but it behaves differently due to the different annealing conditions. So we can change orientation of our domains in space. Quite interesting feature which might be observed in the case of semi-crystalline polymers is when our polymer undergoes crystallization. So when we have a thin films made out of block copolymers, and there is a certain fraction of crystalline polymer over there, we can observe this growth of quasi two-dimensional crystals, which have this sandwich-like structure. We have a polyethylene crystallite in the middle, and the amorphous polystyrene face pushed outward, either on the top or to the bottom of our crystallite structure. And of course, from the point of view of nanolithography, we would like to avoid crystallization, and therefore we have to do our annealing above a certain temperature, which is crystallization, which is a melting point for these crystalline features. But okay, let me skip to, I started with some microscopic data to really show you that the diblock copolymers are very interesting and might be potentially very useful in a future, let's say, nanolithography and microelectronics, because in general we may produce quite unique nanoscopic patterns using this approach. And as you can see, since this is the thermodynamics really follows, I mean stimulates the whole mechanism, it means that this is relatively cheap approach when in comparison to the quite demanding, challenging top-down strategies, for example, photolithography. And what is even more important is that we can produce features which are less than 10 nanometers. So the spatial resolution is quite significant when we use dipole copolymer approach in nanolithography. But right now, I would like to tell you about some different approach to really probe and monitor the morphology of this kind of systems. And this is a very beautiful. I'd like to really show you some basics of this very beautiful paper published in 1993 by Klaus, Schmidt-Rohr and Spies, who introduced this concept of NMR spin diffusion used as a tool for structural studies concerning heterogeneous systems and block copolymers in particular, because block copolymers, due to their nicely designed, nicely defined morphologies, can be treated using this this particular approach, where the NMR spin diffusion can be employed as a tool for domain size estimation of the domain dimensions. And what is even more important is that this is the very unique technique, because we can first of all assess domain dimensions. That's the one thing, and above that, moreover, we can also estimate the so-called interfacial thickness, and this parameter is as the parameter of great importance in microelectronics, because it really determines the sharpness of our structural motifs. So it really determines the eventual feature size produced via block copolymer lithography. And like commonly used techniques like microscopy, either atomic force microscopy, electron microscopy, or scanning, or transmission, they do provide quite nice pictures. However, one is not able to tell anything at all about interfacial thickness using microscopic approach. Even small angle scattering data, they don't provide any information about the interfaces, while NMR does, and it can give you us extra information about the morphology, how sharp is the interface within such systems. Because this approach really relies on the fact that we have two different domains having different mobility, different dynamics. So the molecular dynamics is our, let's say, it really differentiates both subunits within the copolymer systems. Right. So as you can see, this approach is as following: we can introduce non-uniform distribution of magnetization using a so-called dipolar filter pulse sequence, and having, for example, two different domains. One domain is, let's say, a stiff domain, so it's based on the polymer having a high glass transition. So it's at room temperature. This particular polymer is very stiff and rigid component, and while the second component, for example, polyethylene oxide is the, let's say, the soft component, which displays relatively low glass transition temperature. So, for example, -70, -60 Celsius degree. That means that at room temperature, this particular domain behaves as a it's already very viscous medium. So we have two different polymer chains covalently linked together. One is stiff and one is very mobile. That means that one displays very short spin relaxation time, while the second one displays very much relatively longer, much longer T2 relaxation time. So in general, it does have much longer FID signal than the rigid component. And that, therefore, using this kind of trick, we can get rid of the magnetization, which is placed, which is, let's say, placed within the rigid domains. And then in such a way, we introduce spatial inhomogeneities in terms of magnetization distribution within the samples. And Blombergen, he was the first who really claimed that the magnetization, if there is a non-uniform distribution of magnetization within the sample, then we observe that the magnetization via dipolar coupling, it can really migrate like through the sample and levels out gradually. And this process might be described using ordinary diffusion equation, and therefore Blombergen called that process spin diffusion. And tracing what is really going with our NMR signal with time, with so-called mixing time here, we can sample this mixing time and we can observe how our signal behaves as a function of mixing time. We can determine the dimension of our domains, where this epsilon here is so-called, this is like, it represents different dimensionality. If the diffusion is one-dimensional, two-dimensional, or three-dimensional, and it does depend on the domain structure. While the most important parameter here is the spin diffusion parameter, which really signifies how quick, how fast the spin diffusion process takes place. And of course, it does depend on the molecular, on the mobility of our medium, of our material. So in general, the larger is the spin diffusion coefficient, the more rigid is the material. And for the soft components, we observe much lower values of spin diffusion coefficients. But nevertheless, using this simple approach, we can estimate dimensions of this within such a systems. So this is the idea that, for example, we have a rigid matrix and soft cylinders, and introducing dipolar filter, we can initially see that our magnetization profiles here looks like that. So we get rid of magnetization within the hard matrix, while we leave the magnetization within the soft components. And then with a mixing time, we observe the migration of our magnetization and due to the spin diffusion. And that's the opposite scenario where we have the soft matrix and the hard cylinders. So that's the same basics pattern here. And using, for example, carbon-13 observation, so we can observe the signal coming specifically from one component only. So in this particular case, I'd like to show you that we can trace the signal coming directly from the polystyrene phase, which is the hard phase, like for example this blue color phase here. We can observe how this signal really grows with a mixing time, and we can then trace how this signal really behaves during this mixing time here. Of course, we have to also take into account the spin lattice relaxation time mechanics, because both of these phenomena they take place simultaneously. So we have spin diffusion, and apart from that, on top of it we have separately the spin lattice relaxation time. So, but that's not a problem at all, because we can nicely define the spin lattice relaxation T1 constants for our system, and we can really take that into consideration when analyzing our spin diffusion data. So this is the example. We have polystyrene and polyisoprene in this particular case. So again, the same story. We have polystyrene block, which is the hard, let's say, rigid component with a high glass transition temperature. Glass transition for polystyrene is around 100 Celsius degrees. So above 100 Celsius degree, the polystyrene becomes quite plastic, quite elastic material. While, however, below that, glass transition temperature is very rigid, because structural relaxation, I mean, all this segmental reorientations of the polystyrene chains are still freezed in time. While polyisoprene, the second component, it's a very mobile polymer. Its glass transition is around minus 70, I guess, Celsius degrees. So at room temperature, it's very mobile polymer. So that's the point. So we have two different components. Both of them exhibit completely different molecular dynamics. And then we can introduce this concept and try to estimate the domain sizes using spin diffusion and NMR spin diffusion approach. And here you can see that we can introduce a slightly modified model, where instead of using only one component, we have two different components. And the first component is, which I mentioned before, is the one which allows us to define the dimension of hard domain. In this particular case, that is going to be a polystyrene domain, while the second component indicates so-called interfacial domain. So the domain which represents the interface, where so this is the region where both type of polymer species, they coexist together somehow at the interface, and they do interact, and they modify the effective spin diffusion coefficient at this place. So what we can expect that in a bulk system, spin diffusion coefficient for the polystyrene is nicely defined. However, within the interface, where both different types of polymers they interact significantly, so then the effective spin diffusion coefficient has to be and is very much different. And this effective spin diffusion coefficient might be defined using Mellinger formula. And using this simple approach, it's very much simplified, because of course you can expect that instead of having one specific effective spin diffusion coefficient, you rather expect some gradient of spin diffusion coefficients within the interfacial region. And of course, that's probably the case. However, then the model would be quite difficult to really to analyze. And instead, you can analyze your data with this very simple approach, where you.
Jacek, excuse me, 5 minutes only. 5 minutes only.
5 minutes left. Okay, so as you can see, there are two different components. The first component signifies the interface, while the second our face, and you can nicely combine that and compare that with AFM data. We have exactly the same analysis done for a different kind of polymers, polystyrene polyethylene oxide, and we can see that you can nicely correlate microscopic data with the data provided by NMR spin diffusion. Still, we have to keep in mind that NMR spin diffusion gives us an extra information about this interfacial region, which is, for example, for this polymer is around 2 nanometers. So different systems, we have polystyrene polydimethylsiloxane. Polydimethylsiloxane, again, it's a polymer which represents, in this case, the soft component with a low glass transition temperature. And again, we have, using the same NMR spin diffusion approach, we can nicely define both the dimension of our hard face together with the interfacial thickness. And this is very nice. Probably most of you have seen these kind of results. This is also the technique introduced by Wolfgang Spies in 90s. This is Wiese NMR experiments, or wide line separation experiments, where you can nicely separate proton signals using carbon dimension. And you can nicely see that, for example, the signal which represents polydimethylsiloxane has a completely different line width than the signal attributed to the hard polystyrene. And using this Wiese NMR, you can nicely distinguish 2 different subunits, and you can prove and show directly that they do undergo phase separation, and you have 2 different domains having different mobility. Well, I have some other examples concerning polystyrene polydimethylsiloxane, where we studied it because there's very nice, very interesting thing concerning so-called rigid amorphous phase. Because when you deal with the semi-crystalline polymers, there are always 2 different fractions of amorphous, different amorphous fractions. One is called mobile amorphous fraction, and the second is rigid amorphous fraction, which represents the fraction of polymers which are adjacent to the crystalline phase. And we wanted to show to check whether it's possible to really observe and distinguish rigid amorphous phase from mobile amorphous phase. So these are, again, we have done atomic force microscopy to see the phase separation directly. And we used also the dielectric spectroscopy to really trace the dynamics. Here, so-called alpha relaxation or structural relaxation within polydimethylsiloxane component here. So we observe the local reorientations taking place within that chain, polymer chain, and we could distinguish that there are two different fractions. One is assigned to the mobile amorphous fraction and the rigid amorphous fraction. And what was very important and quite surprising for us that when we studied bulk polydimethylsiloxane, it appeared that the same its dynamics is faster within the diblock copolymer system, which was quite surprising for us initially, because in general the trend is that whenever you combine the soft component with a hard polystyrene component, then this stiff domain hinders in general the dynamics of the soft neighbor, while here we observed something opposite. And then what's seen here, that for example mobile amorphous fraction within the diblock copolymers is shifted towards higher frequencies at the same temperature. That means really that our dynamics within the copolymer is slightly faster here, and that really means that the structure of the domains really matter, and that represents the fact that our mobile chains have a different conformation within the copolymer than in the bulk phase, because we can imagine that the curvature of the domain does matter, and in order to maintain the density within the domain, you expect a stretched conformation at the vicinity of the interface, while the terminal side of the chain might have completely different conformations, and that may really introduce slightly different dynamics, and may lead to the faster segmental dynamics within the soft component. That was our assumption. And do I still have some time, or it's already gone?
Thank you. Your time is over.
Okay, so let me maybe skip, and let me thank the people who were involved in all these studies, and I would like to thank Professor Jurga in particular, and all my colleagues and friends, and fundings as well, and also I would like to thank you for your attention.
Thank you.